Welcome to Dentect, the revolutionary website that helps dentists diagnose dental diseases quickly and accurately. As we all know, detecting these diseases early is critical for successful treatment. However, traditional methods of diagnosis can be time consuming and sometimes unreliable. That's where Dentect comes in. With our easy to use website, dentists can upload panoramic radiographs and let our advanced algorithm do the rest. Within minutes, you will receive a detailed detection for the uploaded X-ray. Dental diseases affect millions of people in daily life, and their early detection saves money and time. Dental radiographs are one of the most common examinations performed in dental clinics. What are radiographs? Do they expose only one problem? The answer of these questions is in Dentect. They expose more than one disease, and that was our aim to help dentists find out most of the disease. And according to a study, there is a relationship between the time taken by dentists to diagnose one disease and their time of experience. The result was 42 seconds on average. Another study was made to check the detection accuracy when dentists were under the factor of time pressure. The result was 67% of bone loss and 40% of tooth decay radiographs had missed diagnosis. However, when the time factor wasn't there, the 40 dentists who participated in the experiments gave more accurate results. With the help of machine learning, dentists can detect dental abnormalities faster and more accurately, where in recent years CNN models have achieved the highest accuracy in various computer vision tasks. According to a study done with the help of 3 dentists, their diagnostic performance was improved after CNN revision than before. Our objectives are to save time and get better detection accuracy by developing an application that dentists can use to diagnose specific abnormalities using panoramic dental radiographs.
According to datasets, we use two datasets. First one, Tufts Dental Database, and it contains 1051 panoramic X-ray, and have 5 level of classification. We took last level of classification, and it only contains 300 images that have anomalies with 8 classes. It was unbalanced and gave us low accuracy, as we'll show later in the result. And because of high confidentiality of medical data, so it was hard for us to find another public dataset, so that we collect our dataset from local hospital, and with a group of dental experts, they annotate 733 panoramic X-ray with 6 classes: caries proximal, caries occlusal, periodontal bullous interdental, periodontal bullous interradicular, preapical lesion, and impaction. And that's the annotation sample. Experts draw polygons with 6 different colors, and each color corresponds to different disease. And that's the hex color of the polygons of each disease. As the data distribution show us the unbalancing in our dataset, where the least of them class is periodontal bullous interradicular, and the most is periodontal bullous interdental. And in data preparation, we convert the polygons into bounding boxes, because our task is object detection task. So firstly, we perform color-based segmentation on polygons that we have, then edge detection to retrieve the bounding boxes, but as shown, there is some problem occurred with the segmentation task, and some polygons doesn't detect it and retrieve its bounding boxes correctly. So that by using some morphological operations, the problem is solved, and save the labels in CSV file and change its format according to the model that we will use. And in pre-processing, we use resizing and cropping, and augmentation using RoboFlow. We use sharpening, contrast, brightness, histogram equalization, horizontal flipping, and scaling. And according to system architecture, we have 3 layers: presentation layer and application layers that have web app service API, model architecture, web application, and database layer. And according to application layer, we have input, that is panoramic X-ray image, and after that processing the image, then object detection, then the output is the image with the bounding boxes.
Since our target is to detect dental diseases, we use object detection models. Object detection is a computer vision technique used for locating instances of objects in images or videos. There are many types of object detection models, and we will be discussing two models. Faster RCNN is a two-shot detector where the RPN is used to select possible regions of interest and the CNN is used to classify the detected object. YOLO, or You Only Look Once, is a single-shot detector which draws grids on the image and uses them to draw bounding boxes and calculate the class probability in each location to classify the objects in the image. The metrics used by the object detection models are precision, recall, intersection of union, and mean average precision. The mean average precision compares the ground truth bounding box to the detected box and returns a score. The higher the score, the more accurate the model is. There are two variations of mean average precision, being mean average precision 50, which is used for the Pascal VOC dataset metric, and mean average precision 50 over 95, which is Microsoft COCO dataset metric. The number indicates the intersection over union threshold, which is the intersection of the ground truth and the protected bounding box over their union. The higher the number, the more accurate the detection is. We have tried several experiments on different object detection models, and the best experimental results were viewed on the YOLO Region 5. As shown in this table is the YOLO Region 5 validation testing accuracy on our dataset. The total mean average precision at 0.5 intersection over union was 61% validation and 67.7 testing. And as for the mean average precision 0.5 to 0.95 intersection over union, it was 28% validation and 35 testing. As you may notice, the highest mean average precision for a certain class was the second one, being the periodontal bone loss interreticular, as it was abundant in our dataset, being reclaiming the largest amount of images in our dataset. Second comes the impaction at 75 mean average precision validation, and that is due to the large size of the bounding box, making it easier to identify it. Here is the demo of our website. The dentist can click join now to join our website and signing up using first name, last name, email, medical ID, years of experience, clinic phone, and clinic address. If the email already exists, an error message is shown. After that, he receives an OTP email to identify if it's indeed the correct email address for this dentist. If he is indeed the dentist, he can then register the patient using the data given by the patient, from medical history to phone to the birth date and dental history. And then he enters the ID in the clinic and the X-ray date and clicks on detect. If the ID was wrong, he then re-enters the ID and clicks on detect once again, and is then shown the detection where the bounding boxes are around the object of interest and the accuracy of each The tools we used were PyTorch and TensorFlow as machine learning frameworks, Google Colab as Cloud IDE, OpenCV and implementations for image pre-processing, Mongo Atlas Cloud Database and Firebase Cloud Storage, Express.js and Node.js for back-end server, React.js for front-end user interface. The challenges we faced were that all dental datasets are private, our dataset was unbalanced and of small size, lack of computational power for bigger models, and lack of hyperparameters mentioned in the red papers and articles. We target dental professionals working in clinics and hospitals. What we present with our application are early diagnosis of dental diseases and detailed monitoring and reporting with assistive medical technology.
And thanks for listening.